Hello, this is Tanner Tech, and right now I'm doing a live stream where I will build almost anything you say in the comments. Whether it's messing with electronic components, building a new circuit, you pretty much have my lab at your disposal. So I will be looking at your comments, and hopefully I can build anything you want. Or if you have any questions about electronics, you can put them in the comments, and I'll try and show those questions live. So, let's get started. Tanner Tech, Tanner Tech, Tanner, Tanner Tech, Tanner Tech, Tanner. Hello, this is Tanner Tech. Alright, let's take a look at my lab. Wow, got a lot of viewers already. Ooh. Wow, got a lot of comments already. So, build a reactor. Well, I don't know if I can build a reactor for you. Someone here asked, his name is just User, if I could build a reactor. Now, that's kind of hard. I don't really have the stuff to do that. But I will do something for this guy, Darius Dark Shadow, who wants me to build a flux capacitor. Now, for those of you who don't know, a flux capacitor is something in Back to the Future. And in Back to the Future, it's this thing. It looks kind of like this triangle, and it's in the back of the DeLorean. Sorry, but this flux capacitor that you see is not actually real. Capacitors don't look like that. They look like this. This is my little bench thing, and in here I have lots of capacitors. Here are some electrolytic capacitors right here, and pretty much capacitors just hold a charge. They don't actually allow you to time travel. But I can show you something else cool with capacitors. This is my capacitor bank. I've showed how to do this in a previous video. Okay, someone just asked if I could build a capacitor with flux. So, I guess that's a flux capacitor. Here, I'll try that in just a second. We got some flux right here. Anyway, this is a capacitor bank that I made in a previous video. And here I can actually make big sparks and kind of some big explosions. So, for the person who asked for this, I'd keep watching because it's going to be cool. We're going to plug in this capacitor bank. So, this is my capacitor bank. I'll just fire it up. Let's move my light. Fire it up. Now here we go. This capacitor bank is charging up to pretty high voltage using this little readout right here. Now what I'm going to do is I'm going to touch these two wires together, and hopefully it'll make an explosion. Yeah, for the person who is asking about flux, this is flux right here. Oh, better turn that off. Flux is just this kind of greasy paste, and I'll make that flux capacitor, a literal flux capacitor. Anyway, I will turn this off. Be careful not to touch this. This is 400 volts, very, very dangerous. Whew. That's pretty big. Sorry, it won't help you time travel, but it still makes a pretty cool explosion. Now this not flux capacitor can also do some pretty cool things to solder. Now, keep waiting because I will do an actual flux capacitor. Just hold up a second. Alright. Okay, so this is some solder. This is a piece of solder and my high voltage capacitor bank. Whoo, that was cool. Made a big mark on my desk, but it worked. Okay, so for the people asking, I'm going to make a flux capacitor. We're going to make one. So a capacitor, according to this diagram that I'm about to draw. Oh, awesome. So I will make a Geiger Counter for you, Eddie Van Horn, soon, and we'll test that on the Trinitite you're going to be sending. So a capacitor is pretty much something with two plates inside it. So we've got one top plate, one bottom plate, and both of them are connected to something. And then in the middle, we have something called a dielectric. Now, depending on what a dielectric is, it'll make a different cap bank to a flash tube. I'll do that too eventually. Anyway, This capacitor bank has some kind of dielectric inside, and that is what helps it hold a different charge to do it. So if I take two pieces of metal, let's just say these X-Acto knives, and I put it right here, then depending on how far the plates are from each other and what the substance is in the middle will change the capacitance of it. So, for instance, if we have an electrolytic capacitor like this, these capacitors actually have large metal plates inside them. Here, I'll cut one open. And inside those metal plates, there's dielectric. That dielectric is pretty cool. Let me pop this open. We'll get to your flux capacitor and everything else in the comments soon. Now, I wouldn't suggest you do this. Oh, gross. See that stuff that dripped out of the capacitor right there? That is the dielectric inside the capacitor. Now, I'm not going to peel this open, but there are metal plates inside. Now, don't touch this dielectric. It's made with PCBs. It's kind of toxic. Yep. Alright. So this is flux right here. Now, flux is intended for use with soldering, and I will explain that because when you have a circuit board, and that circuit board has soldering pins on here, then these pins will be kind of hard to solder because when you touch the soldering iron here, the solder won't necessarily flow onto it, and so the flux just helps it flow. So I'm not exactly sure if flux would work for a capacitor, but let's try that out. I'm really liking this idea. So I have my multimeter right here, and on my multimeter it has a capacitance function and a resistance function. So first we need to make sure that this dielectric isn't going to be very conductive, because if the dielectric is conductive, then it won't necessarily work for our project. So I'm going to set it to ohms, and I'm going to stick my multimeter inside this flux. Doesn't seem to be conductive. Now, if I set my multimeter to capacitance mode, and we stick these two probes inside there, the capacitance hopefully should go up if flux makes a good dielectric. There we go. You can see it did change. Not by much. Wait a second. It changed slightly. Alright. So I'm going to connect this flux paste to two separate pieces of plate, and we're going to see if we can actually make a capacitor. So first of all, I need to go get some metal plates, and so hang in there for a second, anybody who is still watching, and I will go find some metal plates to use for my dielectric. Here we go. I think we'll be using heatsink as one of my metal plates for this flux capacitor. This one should work. It's not too bad. And then maybe find something else. Sometimes this stuff's kind of hard. Alright, this metal plate should work too. So, we're going to take this metal plate. Oh, make a 555 timer with vacuum tubes, someone just said. That's pretty much really hard. A 555 timer has like 100 100 transistors inside it. That means I would have to have 100 vacuum tubes. And those vacuum tubes aren't necessarily have the same characteristics as a transistor. And so that may not work. Hello, cool boy dude. Anyway, we've got our two metal plates, and we've got some flux. We're going to make a flux capacitor. Let me grab a tissue real quick. Compressed air expire. I have no idea. So we're going to take my multimeter probes and clean those off first of all. Flux is pretty nasty stuff. Then we're going to take some of this flux and stick it on this heatsink. Now, these are the two plates of my capacitor. Oh. I'll use a sticky note. Not sure what this paper is for. We're going to take this paper, use it to smear some flux on this piece of heatsink. There we go. Now we're going to take... Okay, I see the vacuum tube Joule thief. I'll try that. We may not have enough time in this live stream. So I'll put some flux on this heatsink. There we go. There's some good flux. And we're going to stick a heatsink on top of that. Making sure they don't touch. Oh, too late for that. Ah, dang it, I got it on my hand. Okay, so someone just asked what flux does, and flux is a substance that helps solder reflow. Now I have my soldering iron hopefully heating up so that way I can show you guys what it does. Alright, we're going to keep working on this flux capacitor. So I'll put my aluminum on top of each other. Now we'll take my multimeter and verify that there is no conduction between these two plates. So I'll switch that to resistance. We'll touch one to this plate, one to this plate. It has a high mega ohm rating, but that's fine. That's typical. So now we'll set this to capacitance. Whoa, there we go. There we go. That's pretty cool. See how it jumped up to 283 nanofarads? That's 0.300 nanofarads. That is pretty cool. That means our flux capacitor is actually working. There we've actually got it up to 2 nanofarads. If I press this down more, we can hopefully get some 5 nanofarads. It's kind of touchy. There we got it, 2 nanofarads. So there you go. That is a flux capacitor. That is a literal flux capacitor. I use some flux as my dielectric, and I have my 2 metal plates, and it actually... Well, I just dropped my flux capacitor, and now I got flux in my carpet. Oh! Someone just commented that a true flux capacitor would store magnetic flux by shocking 2 halves of a transformer core with a short coil and trap the flux. Now that's not possible because the law of thermodynamics, or not that, but the conservation of energy states that, actually no. You see, that magnetic flux is eventually going to be lost inside the transformer core, and so it's going to not work anymore. Let's show that flux capacitor in work one more time. So this 0.8 nanofarads that you see on that screen is actually the just straight capacitance of the 2 meter probes. But if I touch one of these probes to this thing, and I touch one of them to the heatsink, we see how it jumps up to about 1.0, maybe like 0.3 nanofarads. So it's not that much of a capacitor, but it's still... Dang it, I keep dropping it. But it still works pretty good. And so there it is. A literal flux capacitor. A capacitor made out of solder flux. Whoever had that idea, that was pretty cool. So I'm going to set that flux aside. And we're going to do something else. So I'm going to clean that off later. Anyway, just because that was a flux capacitor, I'm going to do something cool and play the Back to the Future theme song on this piano. Because on this piano, I just fixed it. This keyboard had broken, and so I replaced the old keyboard, the old control board, with this new control board that has an Arduino and some shift registers, and it connects via a MIDI port to my laptop right here. So here is the Back to the Future theme song. Forgive me if I mess it up, but here we go. There you go. That is the Flux Capacitor. There we go. So we built a Flux Capacitor and played the Back to the Future theme song. So let me take a look at some comments and see what other people have asked me to do, and I will try and do it. Just a second. I'm going to scroll up to the top, and we'll see if we can find any good comments of things to build. So someone mentioned me make a 555 timer with vacuum tubes. That's practically impossible, because a 555 timer, even though it is extremely small, it's one right here. This 555 timer has 100 transistors inside it, so I would need 100 vacuum tubes, and that would be a lot of stuff. So someone is asking if I could build a Joule thief from a vacuum tube, or hook up the cat bank to a flash tube, and see if I can make it flash. Build a ring oscillator. That's what I see for now. So right now I'm going to try a vacuum tube Joule thief. That sounds pretty cool. Actually, alright, just a second. Let's go find a vacuum tube. So this is my vacuum tube stash. Let's just grab one of these things. So vacuum tubes actually use a lot of power. So inside this vacuum tube, you can see that we have a few plates inside here. We have this ring plate around this tiny plate inside. And what happens is there's a little filament inside there that heats up, and this filament emits electrons, and those electrons are drawn to the plate on the outside of the vacuum tube by voltage. Now, the issue with making a Joule thief out of a vacuum tube is that the voltage is too high, and it defeats the whole purpose of a Joule thief. So let's take a look at the circuit of a typical Joule thief. So we have a transistor, and it's typically an NPN transistor, which means we have a base, an emitter, and a collector. And then we have usually a toroidal transformer, and it has two windings on it, and these two windings are kind of opposite of each other. And so typically in a Joule thief, we have this winding connected to this winding, and that goes to positive or something. And we have this winding this winding go to one side of the transistor. We have this side going to a resistor, usually like 1K or something. And then that goes there. And then this goes to ground. And this goes to positive. And this is anything from 0.7 volts to maybe 1.2 volts. Now, inside this Joule thief, the LED is placed across here. Typically like that. And it emits light. So pretty much what this circuit does is, when power is applied, it goes across these two coils, and it forms kind of an oscillator that kind of boosts the voltage of the initial voltage applied, so that way the voltage can run through this LED, and so that makes it so it'll light up even at voltages where an LED won't typically run. Now, the issue with using an old vacuum tube as the transistor inside a Joule thief is that vacuum tubes require large amounts of current to run, and they require a high voltage because they have a very high impedance, unlike this transistor, which has kind of a low impedance on the output. That means in order to get a usable current flow through this vacuum tube, you have to have a high voltage between the outside and the inside. Now, the purpose of a Joule thief is to make it so that way it can run an LED super efficient on a very low voltage, and a vacuum tube is pretty much the opposite of efficient because it wastes energy as heat in the filament, and it is just unable to run an LED. If I hooked up a vacuum tube in the same configuration as this LED, the LED would explode. So it's kind of hard to make a Joule thief with a vacuum tube, but if you want it to achieve the purpose of a normal Joule thief. But you can make a vacuum tube oscillator that is able to oscillate at different radio frequencies and other things. Anyway, let me look at some of the comments and see if I can have anything else. Okay, someone just said that Joule thief is pretty much the same as a vacuum tube solid-state Tesla coil. And that's true, but the purpose of a vacuum tube Tesla coil is to make a magnetic flux around the core of the Tesla coil to create that radio frequency that allows sparks to jump out. And a Joule thief is meant to light a light at low voltage levels. Let me see. So people are asking, what is the source of all my vacuum tubes? Alright. I get my vacuum tubes, a lot of them off eBay. A lot of them I just find. I've actually fixed a lot of vacuum tube things. Ha! Wow, the chat is going crazy now. Let's stop that and let's make a xenon flash lamp with this thing. So I got some xenon tubes, hopefully. Let's go up here. I cannot find my light bulbs. There we go. Hopefully I'll have a xenon flash tube in here somewhere. There you go. Whoever suggested xenon flash tubes, you're in luck. So I have like 3 flash tubes. Those are xenon flash tubes, and they want me to run this on my capacitor bank. Ha! There you go, look it. I can make a flux capacitor out of these xenon flash tubes. It looks like the one from the movie. Okay. Someone asked if I could make an oscillator. A thing that can light up these flash tubes with my power supply. That's what I'll do. Now, what we have is a xenon tube. And I can connect it directly across the leads of this capacitor bank. But if I do this and I charge it up and discharge it, nothing will happen. That is because inside a xenon flash tube, we have the tube, and we have all these gas molecules inside it. But the voltage that is across these that is needed to make a current flow needs to be very high. So even though we have 200 volts across here, or 400 from this power supply, no current is going to flow and no light is going to come out because of just the high resistance inside here. Now if I take another power supply that is, let's say, 100,000 volts, or maybe 30,000 volts, and put it across this xenon tube, then that'll cause the xenon gas inside to ionize, which means it'll allow a current to flow through and light up the xenon tube. So in order to do that, we're going to have to break out a high voltage power supply. So first, let's hook up this xenon tube to the capacitor bank and see what we can do. Okay, everybody is arguing about AI. You hear about that robot? They just made a citizen, and it's the robot that said it was going to kill humanity. Yeah, that's AI for you. I don't know. I think someone just programmed it to do that as a prank. Okay, right now I'm looking for another alligator clip to hold to this xenon flash tube. I used to have like 100 of these things, but they're all gone now. Alright, solder them in a Y, make them all parallel. Oh, that's why my computer was hiding a bunch of them. Just hold up a second. My computer was hiding a bunch of these things. This computer is actually running LMS. That is how I recorded that Back to the Future song. So, we'll take one of these alligator clips and connect it to the other side of the Xenon tube. That way we should have conduction across the tube. And I just got an email. No, this is not going to put glass in my eye, Eddie Van Horn. I should be perfectly safe right now. So let's get my high voltage power supply. I'm looking at this one. And let's fire it up. Now I'm pretty sure this high voltage power supply is what broke my old piano. Oh dang it, my computer. Fire it up again. Alright. This power supply is what is going to shock our Xenon tube into life. I'm going to set it right here. And we're going to connect it to the wall. Hopefully it's not on. I'll actually be connecting it to my variable power supply, so that way I can turn it on and lower the voltage substantially. I'm going to move all of these electronic devices that could possibly break due to the large electromagnetic field created by this power supply on the Xenon tube. Hopefully I don't break my oscilloscope again. Plug that in. Nothing's happening so far. So far, so safe. This is high voltage, kids. Don't mess with it. Now, you'll notice that my setup is kind of not exactly the safest kind of setup. Well, it should work. I'm hoping this doesn't actually break my camera too. This may actually blow up. So, just warning everyone. Gotta find some more of those alligator clips. I really need to clean my lab. It's kind of hard, though. Don't really got any time for that. Oh, want to move my multimeter. These things can kill a multimeter. Connect one of these here. I'll connect this wire, which is the ground of my high voltage power supply, to one side of the Xenon tube. And we'll connect the high voltage wire to another side using one of these. One of these little things. So, really hope I don't break my power supply. Let me get a screwdriver to hold this with, so I don't get myself shocked. We'll connect up my screwdriver to the power supply. Hopefully I won't get shocked from this too. Alrighty, I think we're just about ready to start this thing. First of all, let me confirm that this power supply works and it indeed creates high voltage. Oh, there we go. That power supply definitely works. Creates a high voltage. So let's charge up this cat bank. Alright. Everybody who's watching, stay tuned because in just a second I'm going to light off this Xenon flash tube. We're just about at maximum voltage. Alright. Here goes nothing. 3, 2, 1. Nothing happened. Maybe I don't have enough power. Maybe I just burnt out my tube. Doubt that though. Well, it's charged. Let's see if it works now. Okay, that's interesting. I can't get this Xenon Tube work. Okay, someone just asked what kind of PS power supply I have. This is my homemade capacitor bank. You can find it in one of my previous videos. But this capacitor bank is pretty much able to generate a high capacitance of about 400 volts. And I think it's like 1500 microfarads. So that way it'll kind of explode if I touch these two wires together. And what I'm trying to do is use a high voltage power supply to ionize the gas inside the Xenon tube. And I've been able to do it before, but it just seems to not be working right now. Let's try that again with maybe a different Xenon tube. Sadly, though, I'm going to have to discharge this capacitor bank. So, watch out. Yeah, I tried to trigger it in the middle of the tube. It didn't work. Watch out. Whew. That was a big explosion. Look it, I've welded my pliers to my Xenon tube. What a surprise. Look it, it's completely welded. Wow. Take a bath in my toaster. Heck no. Look at that. It got welded on. Alrighty. This Xenon tube is not working for me. Now it's welded. It looks like the tube is kind of fractured. Yeah, it's a spot welder indeed. I don't know. Let's try a different tube. Maybe this one will work better. Strip it first. Alright. I gotta connect up this thing. For the person who asked for this Xenon flash tube thing, I'm really going all out on this. It's not working. Okay. We're charging it up again. Wait a second. Yeah, this will work. This is kind of a interesting setup. There we go. Okay, so we're going to try and light up this flash tube again. Hopefully you can see it. It's right there. We're going to charge up this. You can see the voltage is rising. And we'll try and set off this tube again. This is a brand new tube. I'll set my power supply to a lower power level. Hopefully we can get a discharge now. Okay. Ready? 3, 2, 1. Oh, there we go. There we go. There we go. Did you go? Who all saw that? Nope. That thing just worked perfectly. Comment if you actually saw that light, because I'm going to do it again just in case anyone didn't see it. Okay, I'm going to set off the light again. Tell me if you guys saw this thing. Alright. Okay, stay tuned, because I'm going to test it again. In 3, 2, 1. Okay, you all see it that time? Alright. That's the best angle I'm going to get. I'll turn off my light. Okay, hopefully you guys can see it this time. It takes a while to charge up this capacitor every time. We're going to set off the Xenon tube again. Now this is not actually really good looking at it like this, so I'm going to look away. Stay tuned. This is the Xenon tube right there. 3, 2, 1. Okay, do you all see it that time? Okay, comment if you just saw it again. Awesome. Cool. So that means my purpose here is accomplished. I'll fire up the lights again. There we go. We set off a Xenon tube successfully. So whoever asked for that was pretty cool. Nice. Now all you gotta remember is after this power supply has discharged, and you can actually see how much it discharged because this thing went from all the way to red to all the way right here, and that's how much current went through the Xenon tube. Now you don't want to do this too much, it could blow it. But anyway, I'm going to finish discharging it. Oh, that tube's hot. Anyway, that tiny tube is what actually created that flash. It's pretty cool to think about. So, comment what you want me to do next. I know a lot of people have been commenting what they want me to do, but I've kind of forgotten over time. So, put a comment what you want me to do. What do you guys want me to do now? Geiger counter. Well, I've already made one. It doesn't work that well. I'll go find it. Alright, here we go. Wait, okay, so someone said it blacked out my camera. What does that mean? Okay, put 10 resistors in parallel and kill them and show how a GFCI works. And then someone asked for a Geiger counter. So this is my Geiger counter that I made in a previous video. It has a Geiger tube right here. I'm not sure if this is a defective Geiger tube or it doesn't work as well or it doesn't have the right composition of gas inside. This is a Soviet-Russian tube. What I've got right here is I've got my transformer. I've got an oscillator with a 555 timer, and what this does is it pretty much takes about 9 volts, it boosts it all the way up to about 400 volts, and then that is reduced, actually it boosted up to like 600 volts, and that is stabilized by these 4 100 volt Zener diodes and a voltage doubler, and that gives the charge for the tube to run, and whenever a particle hits this tube, it causes current to flow through this piezo buzzer and down here. Now, my issue is I can't actually, you can hear the clicks on this piezo buzzer, but it's so quiet that you can't really hear through the camera microphone. Now, I've tried to put a transistor amplifier on this, but for some reason the clicks go away. So, I'm going to try and get a stronger Geiger tube that has a better chance of letting larger amounts of current flow through it so it can actually trigger a transistor and work better. But anyway, that is my Geiger counter. If you want to see it actually working, you can check out a previous video. Right now, I'm actually working on a design for a better Geiger counter, and I'm ordering a better Geiger tube, so that way it'll work. Okay, someone just asked if I can make a Geiger counter with a neon bulb. Let me find my thing of light bulbs. So I've got a neon bulb somewhere in here, right here. Now, inside this neon bulb I'm pretty sure there's a radioactive source inside here with the neon. And so in the neon bulb, that little radioactive source actually causes the ionization of the neon gas in order for it to light up at such a low voltage. So I'm pretty sure that there is a radiation source inside there. I'm not actually sure. I think I read somewhere inside the comments. Yeah, Eddie Van Horn is sending me some uranium. That's pretty cool. And so I'm going to make a better Geiger counter, and hopefully I can make a better one to test with Eddie Van Horn's uranium. Okay, let me take a look at some of these comments. Put 10 resistors in parallel and kill them. Alright. Let's take some resistors. Now, resistors, when you put them in parallel, they'll get smaller. And so what I'm going to do is I'm going to find some relatively large resistors. Maybe somewhere in the range of 100 ohms. And if I put 10 100 ohm resistors in parallel, shocking, we should get kind of an explosion. Let's try, I haven't used these, 180 ohm resistors. So if I put 10 of these 180 ohm resistors in parallel, then that should bring it down to about 18 ohms. And if I hook it up to my power supply right here, which can supply 12 volts, like 55 amps. Let's do some calculations. So we have an 18 ohm resistor, which is the equivalent resistors if I put those 10 in parallel. Now 18 ohms times the current equals voltage. Now, voltage is going to be about 13.6 volts. So whatever 13.6 divided by 18 is how much current is going to flow through all these resistors when I put it across 12 volts. So someone do the calculations real quick. I don't want to go get my calculator. What is 13.6 divided by 18? Put it in the comments real quick. I will blow up something. I just need 0.755. Thanks, Bryce. Yeah, that's not going to be enough current to really blow these things. Let's try smaller resistor. Let's try a 27 ohm resistor. This thing should pop when I hook it up. Now, I was going to use 180 ohms, but according to that calculation, we're not going to get a big enough explosion out of this. So let's get 10 of these. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoever suggested this, you're wasting my resistors. We're going to put all these in parallel. This may start to smoke when I hook it up. Alright. This is not going to be pretty. Well, actually, maybe. So we've got one pack of 5 resistors. Now let's make another thing of 5 resistors. Now I'll put these two things of 5 resistors together to get our 10 resistors in parallel. Now we're going to take these 10 resistors in parallel and hook them up to my large power supply. Now, if you haven't seen in my previous video, I made this power supply that can provide 12 volts at a very high current. I'm going to hook up my alligator clips to this, and I'm going to see what happens. I'm not going to hook them up to AC. I mean, I could do that, but I just don't have a plug. Even though I have this plug right here, it's got a fuse inside it. I'm not going to break that. I actually don't want to blow my fuse out right now, because I'm trying to live stream here, and I don't want to have my power go out during the live stream. So hopefully this should work. We've got our resistors right here. Let me get a metal tin so I don't burn a hole in my table, or a heat sink at least. We're going to set this up right here. I'll use this thing to hold it. We may get some fire when this starts up. Alright. Can you all see the resistor pretty clearly? Okay. Goodbye, resistors. Okay. Countdown in 3, 2, 1. Goodbye, resistors. Whew. There you go. Bye-bye, resistors. If you look right there, these resistors are completely smoked. That's hot. Alright. Alright. Those resistors are no longer with us. They are no longer alive. Ah, all this is hot. That's a lot of current. That was a lot of current flowing through those resistors. So we've got our 27 ohm resistors all put in 10. So that's 2.7 ohms. Here's a second. I know you want to see a show, guys, but we got to do some math to keep this electronics related. We got about 2.7 ohms, because that is the same as 10 27 ohm resistors in parallel. And so we got 2.7 ohms times current equals the voltage, which is 13.6. I need someone to do some math again. So do 13.6 divided by 2.7. Please, someone? Wow, 50.37. That means this power supply is running at its max supply of 50.7 amps. That, dang it, Christopher. So we got 50.7 amps running through this. Now that times the voltage is 13.6 times 50. Someone do that, please. 13.6 times 50.7. Can someone do 50.6 times 13.7? Because that is how many watts went through these resistors. 689.52 watts. So we had about 700 watts flowing through resistors. And each of these resistors is a quarter watt each. So that times 10 is 4 watts. No. A quarter watt times 10 is 2.5 watts. So we have even less watts. And so we're overloading these resistors at hundreds of times their rated wattage. And so that is pretty cool. Now my whole room smells like burnt resistors. Alright, you got your resistors, and now my bedroom stinks. Congratulations. So, what do you want to see next? Alright, someone said they want a capacitor blow up. Alrighty. Might as well. We got some capacitors right here. I hate these things. They smell so bad when you blow them up. So this capacitor is rated for 16 volts. I'm not sure I'm going to be able to blow that up. We're going to try to get a lower voltage capacitor. This is 10 volts. We should get some good stuff out of this. So we're going to take this capacitor, we're going to hook it up backwards, because that is how you pop these things. My room's going to smell so bad after this. So this stripe right here is negative. We're going to hook up positive to that. This stripe right, the lack of a stripe right here means positive. We're going to hook that up to negative. This has got to be backwards. This is our capacitor. Hook it up to my Variac. I'd rather hook it up to this. Okay, here we go. We've got 1 amp flowing through it. Right now it's boiling inside. Oh! Whew. Wow. That broke my tripod. Whew. That is, yeah, I'm fine. That was a pretty big explosion. Turning that off right now. Wow. Hey. Yeah. This is like Electro Boom. That was my capacitor right there. Or what's left of it. As you can see, everything's gone. My hands are covered with this fluff in the inside. Let's clean that off with a tissue. So yeah, that was... Alrighty. Well, that's my last capacitor explosion for this video. Don't want to get the YouTube AdSense revenue revoked for content like that. My room smells bad now. But anyway, that's pretty cool. Alright, what should we do next? No more capacitor explosions. That was not good. If you look right there, that's actually where the capacitor exploded. That, actually, I think right here is... See that? Look at... That is where all the boiling PCB flew out onto the screen. That's something. It actually could be right here, because there's a chunk missing of my desk right there. So, we got a lot of stuff that popped. Makes for some pretty interesting content. So people are saying that I should do a GFCI, make a frequency counter. Alright, so I've got my stuff up here. These are all my components. I actually got these things from LCSC, which is a really cool company. And I've got some of these little display chips. I've got some 7-segment display counter chips right here too. So what I'm going to do is I'm going to make a frequency counter later. Now this frequency counter is going to be used to find the frequency, different electric components, and I'm still working on this frequency counter. It may take a little while to make. But yes, I will make a frequency counter in a later video, and I will for sure do that. A function generator. Alright, let's try it. We're going to be using a 555 timer or something else, because 555 timers are pretty cool. But first, someone asked about a GFCI. Now, I admit I don't know everything. Now, I'm not sure how a GFCI works. I know that we have a plug on one end, and that plug has 2 wires coming out of it, and that goes to the mains. But what happens in one of these plugs is if you drop your toaster in the bathtub, and your toaster is plugged in here, you're going to be grounded because all the metal pipes in your house are grounded. Now, this ground, what's going to happen is we have a live and neutral wire, and what's going to happen is this live wire is going to touch the water inside your bathtub, and then you're going to be sitting in that water, and this water is grounded. And then if a live wire goes in your bathtub, and the current's going to flow into the water and through you into ground, and that's going to electrocute you. So the purpose of a GFCI is to stop that as soon as it sees a current flowing to ground. So the current is going to rise like this, and what the GFCI is going to do is it's going to sense when the current starts to rise between live and ground, and it's going to immediately kill the circuit, shut off the breaker. And so I'm pretty sure there's some kind of current sensing circuit inside here, using a resistor that's in between live and here. It's also powered by neutral. And what's going to happen is this is just going to shut off the GFCI if the current gets too high. So I don't actually have a GFCI in front of me, but I'll do that later. Show us inside your lab bench power supply. Yeah, I've fixed this before, but right now it's got a bunch of junk sitting on top of it, and I don't really want to crack it open right now. As you can see, we have like 10 screws on each side. And so I've already popped this open once before. Pretty much all it is a big transformer inside it. Not much else. If you want to see the inside of a cool power supply, let me grab it. Here we go. This thing is old. This thing is from like the 50s. But it's a heck of a lot cooler than other power supplies. Just a second. Hold up, hold up. I'm just looking at all your comments right here. Alright, just a second, hold up. Oh, you've taken apart 2 of these supplies I hear? A 2-transistor FM radio. There's a lot of cool suggestions inside here. An H-bridge circuit. Hold up, I'm taking a look at all your comments. Okay, anyway, this is a power supply. I'm not going to show you the inside of this power supply back here, because I'm too lazy to take that apart. I'll show you inside this power supply, though. This power supply I found at a garage sale from, like, the 50s. It's called a Senko, I'm not sure. This is a Senko DC power supply. We've got the AC output and a DC output, and this variable voltage controller, so we can set the voltage inside here. We've even got an old fuse. Now, the cool thing about this is if we pop it open, look at this rheostat. This thing is awesome. When we turn the knob, you can see that this moves like this. And so, that will change the resistance of this resistor based on this tab, and this tab. Now the cool thing about this rheostat is that it can handle huge wattages. It can probably handle like 30 watts probably, and it will still be pretty good. This is a lot better than some other resistors that are inside there. They can only handle a few watts. So I can turn this and it will just adjust the voltage coming out. Now this power supply doesn't work exactly. For some reason, whoever wired it or changed the wiring messed up. This tab of the rheostat isn't even connected. And the way it's wired up, it can't even change any of the voltages coming out of here, even when it's running. So this isn't a very good power supply right now. But I'll eventually make it. Right now I'm working on a video. If you look back here, you can see something pretty cool. Now right here, this is called selenium rectifier. You can see it right back. You can see it right back there. And this selenium rectifier is pretty cool because it just shows how old this power supply is, because the selenium rectifier was actually used in many vacuum tube circuits. And what these selenium rectifiers do is they're able to rectify the voltage. Now this huge selenium rectifier is not very efficient, and it probably has about the same characteristics as one of these diodes that are extremely small. So we've got this tiny diode, and we've got this huge selenium rectifier. That just shows you how much technology has advanced in these past few days. What happens here is the current will flow through the selenium rectifier like a diode, and it'll cause the AC current coming out of this transformer to be rectified to DC current. So, sorry I couldn't open this power supply. I just didn't feel like it. But I opened this power supply, and this one I think is a lot cooler than this power supply, just because of the old technology inside it. Okay, I'm getting a lot of awesome suggestions, but this live stream is not going to go on for infinity, which is how long it would take to do all those. So I may do another live stream later that tries to do all of your ideas. So let me get a sticky note and write all your ideas right here, so I can remember and get prepared for my next live stream, so that way I can have some circuit diagrams and stuff available for you. So just list off all your ideas real quick. I'm going to write them down on this piece of paper. So ideas for my next live stream. Make a toaster. Interesting. So 4-bit transistor adder. Alright. No, I actually don't have any Nixie tubes. I'd really like to get some. Right now I'm just scrolling up through the comments. A 2-transistor FM radio. Alright. A lab bench power supply with one of those eBay LEDs power supplies. I actually, for the shrimp who just said that, I may actually make a lab power supply with that cool one, because it has a pretty cool case, but it's not very useful right now. Someone mentioned an H-bridge circuit. Someone mentioned function generator and frequency counter. GFC. Microwave transformer. Sorry for my writing. Alright. Arduino Geiger Counter. Ring oscillator. Okay, see, this is why to build all these things would take me a long time, so I'm going to have to save this for some other live streams. I'm going to have to go do some other stuff soon, but anyway, I'll save this sticky note with some of these things that you want. Let me do one final thing. So just one more thing I should do before I close off this live stream. One more thing that doesn't take a long time to do. An AI takes a long time to do, Darius Dark Shadow. Multimeter, yeah. Oh, you can send some Nixies. Awesome. That would be pretty cool at Event Harm. Nixies would be awesome. I'd definitely do something. Make a multimeter that displays reading on a CRT. Actually, over here, I've got a CRT. That would be awesome to build. Check that out. This is an old CRT from a television. That would be the coolest multimeter that displayed something on this old CRT. Blow up? No, I'm not going to blow up another cat for the person who just commented that. So we can blow up a speaker. I don't have a powerful amplifier right now, so I'm not going to do that. With a Variac? I don't know. Perhaps. Sorry, it may seem weird for the people who are watching this live stream later because I'm just reading comments right now. A volume knob? A volume knob uses one of these potentiometers up in here. We got a... yeah, here's a potentiometer. These potentiometers are what make up volume knobs. These things are pretty cool. You can turn it and it changes the resistance inside here. Oh, battery soldering iron. We got it right on top of my oscilloscope. This is my battery soldering iron right here. Turn it on, heats up, and solders some stuff. Volume knob. Pretty much it's like that variable resistor I showed in my power supply. And so, pretty much what happens is the resistance changes between this one and this one, and this one and this one, as you rotate the volume knob. That change in resistance causes a change in voltage across them, which is able to control the volume. Someone said to blow up a speaker. Now, I would do that with my Variac or a high-power amplifier, but not right now. You know what, actually, one more thing I want to show is this cup full of iron filings. And I found these iron filings. But it's pretty cool because if you... not sure how well you can see that. But if you move inside here, you can see that magnet underneath change. The iron filings look really cool. You have a magnet. A Variac? Yes, a Variac is a variable transformer. This is my Variac over here. I actually made an entire video about Variacs. Make an oscilloscope from an old portable TV. Yeah, I could do that. I actually have done that before. Oh, cast a toroid. Yeah. So, a toroid... sorry, I'm switching subjects all the time. So, this is a toroidal transformer right here. Oh, my room smells so bad like capacitor smoke. That's my dog. Anyway, this is a toroidal transformer, and pretty much what this is this thing cast in some kind of epoxy or something, and it's full of these iron filings, and allows it to conduct electromagnetic flux around without losing anything to eddy currents. And so I could take these filings, but I don't have any epoxy with me right now. Actually, I do have a 60 Hz 120 volt toroidal transformer, and that's in this Variac. So inside the Variac is a transformer, and it's toroidal. It's huge. That's why this thing weighs so much, because it's all iron inside. I'm not sure if you can see it through these cracks, but yeah, the toroidal transformer is inside there. That's about the only one I have right now, though. No, I don't have any wrapped in tape. Yes, it is ferrite. Alright, here, let me go get my oscilloscope that I made from an old TV. Not even sure if it works. Here we go. This is a flashback from a long time ago. This is my old CRT oscilloscope. And this thing is an old CRT. Pretty much I just took it out of the TV and I glued it onto some cardboard. This thing is not the prettiest in the world, but we've got the flyback transformer and stuff. And I've actually taken on these two wires, and these go to the audio output. I'm not even sure how to put this back together anymore. I'm not even sure if it's still connected properly. Yeah, I made a video about this that shows this old Crt oscilloscope quite a while ago. So yeah, that thing's old. If you want to watch that video, I'll put a link to that in the description. Alright, so that was my live stream. I think I got all your suggestions right here. I think that was a pretty successful live stream. Yeah, I carry Eddie. Anyway, I've got your suggestions. I'll try to do this in my next live stream. For now, thanks for watching here. Just a second. Alright, so bye everybody. That was a pretty cool live stream. We almost had a few near-death experiences with that capacitor explosion. But overall, that was a pretty cool live stream. I got all your suggestions right here of what you want in the next live stream. I'll try to get some components together and some other things to do these projects on a live stream, or do them in an actual video. Now, some of these projects take too long to do in a live stream, and maybe sometime when I have a bunch of extra time, I'll actually build one of these projects in a live stream. But other than that, thanks for watching. Stay tuned for next time.